Okay, in this video we're going to be continuing the discussion of finding extreme values of a function. So in the last one we looked at how to find local minimums and local maximums. This time we'll be looking at how to find the global minimum and global maximum. So the difference is that for local minimum the function value just had to be smaller than the function values at nearby points. For a global minimum, it has to be the case that the function value at that point is less than or equal to the function values for all x, not just nearby points. So similarly, for a global maximum, we would have that instead f of p is greater than or equal to f of x for all x. So the picture is that we have some function like this, and I mean we have a local minimum here, for example, but over here is where the global minimum is, because it's an even lower value of the function. So the question is, how can we find the global minimum or global maximum? So in this case, we see that the global minimum occurred at a critical point. So the global minimum was also a local minimum. And in general, that's often going to be the case. The candidate points for a global extremum are the local extreme values in addition to any endpoints of the interval. So for example, in this graph, the global max would actually occur over here, which is not a critical point, but it is an endpoint of the domain of the function as I've drawn it. So the candidates for a global max or min are critical points and endpoints. So we can use this fact to try to find the global max and global min. But first there's another question we have to answer. Is it always going to be the case that there is a global maximum or global minimum? So there's a theorem called the extreme value theorem, which says that if f is continuous on a closed finite interval from, sorry, I guess you can't see that, finite interval from a to b, then f has a global min and a global max on that interval. So this tells us that if the function is continuous and defined on a closed finite interval, then we can find a global maximum and a global minimum. If these two conditions are not satisfied, then that's not necessarily true. For example, if we have a discontinuous function like this, then there's no global max, because the global max should have been at this point here, but that point is not included in the domain of our function. It never actually reaches that, so because of that, there isn't the largest value the function takes. It does still have a global min, though, down here. And notice that that is still a critical point because the derivative there would be undefined. So it still satisfies this criteria here, even though the conditions of the extreme value theorem are not satisfied. So another example, if the domain is not closed, so let's say we have an open interval instead, so we do not include these endpoints, then this function has no global max or min, because the global max should have been this point on the far left, but that point isn't included in the domain. And similarly, the global min should have been over here, but that point was excluded. So before we start looking for global extrema, we should first ask ourselves, do we know for sure that they exist? If the function is continuous on a closed finite interval, then we're certain we can find both a global max and a global min. So how do we go about doing that? Well, given a function, we find all its critical points, we find all the endpoints, we check the function values at all those points, and then just check which one has the largest function value, that will be the global max, which one has the smallest function value, that will be the global min. So let's take a look at an example. Suppose we want to find the global max and min of the function f of x equals x plus 1 divided by x on the interval 1/2 to 3. Well, first we want to find the candidate points for where the global max and min could be. So we first find critical points. So critical points, we have f prime of x equals 0. The derivative of this function is this. This equals 0 implies that x is equal to 1. Now there's other critical points. X equals -1 is a critical point, and also x equals 0 is a critical point because the derivative is undefined there. But notice the domain of our function is only 1/2 to 3, so points outside of that we're going to ignore. So our only candidate point is x equals 1. So now we have 3 candidates for global extrema. And so these 3 candidates are the endpoints, x equals 1/2, x equals 3, and the critical points, in this case just x equals 1. So all that remains to do is see what are the values of the function at these 3 points. Well, f of 1/2, if we plug in 1/2 here, we'll get 1/2 plus 2, which gives us 5/2. F of 1 is going to be equal to 2, and f of 3 turns out to be 3 plus 1/3, which is 10 divided by 3. This number is bigger than 5/2, so this is the global max, and this one is the global min. So the global minimum occurs when x equals 1. The global maximum occurs when x is equal to 3. Now if I were to change this interval to something like 1/2 to 3, but not including the endpoints, or not including, say, the right endpoint, then none of this analysis changes, but the point is then this would not be a candidate for the global maximum because we're not including 3 anymore, and so we would conclude there's no global maximum because in some sense it should have been at 3, but that point was excluded from our domain. And notice that in this case we no longer have a closed interval, so the extreme value theorem would not apply. Okay, so next thing I want to do is go over some example of optimization word problems. So in this case, you're given some information about a situation, and you have to find somehow parameters in the problem that give the optimal or best solution, and that usually means finding the maximum or minimum of some function. So there's a general procedure to these sorts of problems. First, you'll want to find an equation for what you want to maximize or minimize. Then the next step will be to get that equation in terms of only one variable. Sometimes that equation that you start with has more than one variable. In that case, there will be enough information in the problem to get it down to just one. Then you perform the optimization, meaning that you take the derivative and find max and min values. And then the last step is to determine what the solution to the problem is based on that. So let's see an example of this in practice. So let's suppose we have a company which is producing cylindrical objects. It's going to have some height h, some radius r, and what these values are is to be determined. So the top and the bottom of the can are going to cost 50 cents to produce for centimeters squared of material that we use. The side of the can costs $1 per centimeter squared to produce. And the question is, how can we find R and H to minimize the total cost that we have to pay, given that the volume of the can has to be 10 centimeters cubed? Okay, so the first step is to write down what we want to minimize. In this case, we want to minimize the cost. So let's write down a function for the cost. So C is going to depend on R and H. So we have the cost of the top and bottom of the can. I'm going to multiply by 2 since it's the same for each, but we have 2 of them. And so the cost per centimeter squared is 50 cents. And then the area of this side is going to be pi r squared. So this term takes into account the cost of the top and bottom. We also have the cost of the sides. So the perimeter of the circle is 2 pi r. Then if we multiply by h, we get the surface area of the outside of the cylinder. So we'll have 2 pi r h. Then we have to multiply by the cost, which is 1. So we get this equation for C. But notice, C has an R in it and also an H in it. So we have 2 variables. That makes it difficult to make progress. So what we have to do is get it down to just one variable. So the way we can do this is we have a formula for the volume. It has to be 10 centimeters cubed. And we know that the volume of this cylinder is pi r squared h. That means that h is equal to v over pi r squared, and we know v is equal to 10. So if we plug this back into our equation up here, that means that c is equal to pi r squared plus, if we plug in this for h, it looks like we'll get 20 divided by r. So now that we have this, we can take the derivative, find the critical points, and so on. So c prime is equal to 2 pi r minus 20r to the negative 2. We want to set this equal to 0. That means that 2 pi r is equal to 20r to the negative 2. Or in other words, r cubed is pi over 10. So r is equal to the cube root of pi over 10. Let's see, have I made a mistake here? I have something different in my notes, but I don't see that I've done anything wrong here. Let's see. 20r to the negative 2 equals this. We divide by the 2 pi, we get 10 over pi. Okay, yeah, so this should be 10 over pi. Sorry for that. So we get r is equal to cube root of 10 over pi. And this is a critical point. So there's also going to be a critical point when r equals 0 because the derivative is undefined, but that's not really reasonable in the context of the problem because we're trying to have r be the radius of some can. If r is equal to 0, then we wouldn't have an object at all, so that wouldn't really make much sense. So we're going to assume that this is our only critical point that's feasible for this problem. Next, we want to make sure that this is actually a minimum of the cost. We can do that by finding c double prime. That turns out to be 2 pi plus 40r to the negative 3. C double prime of this critical point works out to be 6 pi if you do some arithmetic. This is greater than 0. So that means that cube root 10 over pi is a local min by the second derivative test. And so from this, we can conclude that the optimal dimensions for the can are r equal cube root of 10 over pi. Then if we plug back into this formula here, you could figure out the corresponding optimal value for h. That turns out to be also cube root 10 divided by pi. Although, as I recall, there may have been a mistake in my notes in that calculation. But basically, we're just taking cube root 10 over pi and plugging it in right here. Okay, so I'd like to do one more example of an optimization problem. So let's suppose the sum of two numbers is 50. And we want to maximize their product. So in this case, let's write down an equation for what we want to maximize. It's xy. And we'll call this P because it's a product. And again, notice that we have two variables in our equation, which is problematic. So we want to get rid of one of them. We can do that using this first condition. The sum of the two numbers is 50. So x plus y equals 50. That means that y is equal to 50 minus x. Plug that in over here. We get 50x is equal to p. So now if we find the critical points, we get p prime is negative 2x plus 50. This equals 0 implies that x is equal to 25. And so that means that y is also equal to 25. And we can check if we take the second derivative that this will actually be a maximum. You can use the second derivative test, or you can just look at the form of p. We see that it's a parabola, which is a negative x squared term, means the parabola is shaped like this. So that means that this critical point has to be a maximum. And so this is a common feature when you want to maximize things like this, is that it turns out the best thing to do is to take both x and y to be the same value. Okay, so of course these optimization word problems come in a lot of different forms. So it's good to get do some textbook problems or something like that to get some practice with this. But they all follow the same procedure. You write down what you want to minimize or maximize. You'll have some condition that lets you get that equation in terms of just one variable. Then you find critical points, check to make sure that they're a maximum or minimum, and then figure out what the other variables in the equation were.